In this video, we are going to look at radical functions, and simplifying radical functions. So what is a radical? Radical is a function written in the form of nth root of a. This is a radical. The number in the pocket is called index. The number inside my radical sign is called index. And the number inside is called radicand. Radicand, index and radicand. Okay. If there's no index, it is supposed to be a square root, a 2 in there. For example, square root of 81, there's nothing in the pocket. There is a hidden 2 in here. That's not necessary to write. So when the index is missing, it is automatically considered that it's a 2. Square root of a number a is the number that was squared to get a. Principal and negative square roots. If a is a non-negative number, then square root of a is principal square root of a, and negative root a is a negative square root of a. Remember, square root of a number is always positive. Very important. Square root of a number is always positive. For example, square root of 81 is only 9. It is not plus or minus 9. Keep in mind. Square root of 64 is only 8 because 8 times 8 gives you 64. It is not plus or minus 8. And there's a reason why we will discuss in a few minutes. So remember, the square root of a number is always positive. What exactly does taking a root means? So let's look at some examples. So I'm going to do prime factorization of 64, the radicand, the number inside. What does square root of 64 means? That means how many pairs of 2's do we have inside? That would be square root of 64. So for each 2 2's inside, 1 2 will come out of the radical, which will be 1 2 comes out, another pair 2 comes out, another 2 comes out. So this is how many we're looking for in a group. How many groups of 2's do we have? 2 2's do we have inside? We have 3 groups of 2 2's each, and 2 times 2 times 2 is 8. So square root of 64 is 8. The next one, we're looking at cube root of 64. Cube root means we're looking for pairs of 3 now. Groups of 3 inside. So for each group of 3 2's inside, 1 2 will come out. There's 2 groups of 3 2's each, so 2 2's come out. For each group of 3 things inside, 1 will come out, okay, out of the radical. So 2 times 2 is 4. Cube root of 64 is 4. That means 4 times 4 times 4 gives me 64. And square root means 8 times 8 gives me 64. Next, we're going to talk about fourth root of 64. For 4 2's inside, 1 will come out. So 1 2 comes out for 4 2's inside. But these two poor 2's are stuck inside. And there would be just 2 times 2, 4 inside, and it's a fourth root. So that's how we can simplify fourth root of 64. Next, we got fifth root of 64. For 5 2's inside, 1 2 will come out. Fifth root of 2 is what we are left with. Now we don't have enough to bring that lonely 2 out. It didn't have a group of, it needs to have a group of 5 to come out, but we don't have a group of 5, so it's stuck inside. Next, we have sixth root of 64. So for 6 2's inside, 1 2 comes out and nothing is left inside the radical. Seventh root of 64, for 7 2's inside, we need to be able to bring 1 out. It's not really, there's not enough groups. There's not enough 2's to have a group of 7. So that means it cannot be simplified anymore, and that's how we will leave it. And let's think about solving these two equations. X squared equals 25. So how many possible answers here? There's 2 possible answers. X can be a positive 5 or a negative 5. There's 2 possible answers here, a positive 5 and a negative 5. Both of these will make the equation true. And the next one is square root of 25 is equal to x. In this case, there's only one possible answer, which is x equals 5. We don't have 2 possible answers here because we just said The square root of a number is always positive. So square root of 25 is not a plus and minus 5. It's only a positive 5. Remember that square root of a number or any even root of a negative number is not a real number. So square root or any even root. So we're not talking about just square root. We're also talking about 4th root, 6th root, 8th root, 10th root, 12th root. Even root of a negative number is not a real number. On the other hand, cube root of any negative number is always real. Why? Because think about square root of negative 81. Can you think of any number that you will multiply with itself to get negative 81? Not really, because if you're about to say, well, 9, then 9 times 9 is positive 81, not negative 81. If you were going to say negative 9, then negative 9 times negative 9 is also a positive 81. It is not equal to negative 81. So square root of a negative inside an even root is not a real number. So when you have an even root and negative radicand, so even root and negative radicand, so this is going to be not a real solution here. So this is going to be not real. Okay, keep in mind, even root and a negative radicand, it's going to be not real. And that's not the case with the odd roots, with the cube root, 5th root, 7th root. This is not the problem, because let's think about cube root of negative 64. What number multiplied with itself 3 times will give me negative 64? That's negative 4, because negative 4 times negative 4 times negative 4 is negative 64. So there we go. Let's go ahead and simplify some radicals. Assume that all variables are positive numbers only. This is important because if variables are not positive, then there's something else we need to think about, which is absolute value bars, which is coming soon later in this lecture. So let's think about square root of 64. What number times itself gives you 64? Well, that's 8. Cube root of negative 64? Yes, that's a real number. That's a negative 4. Because cube root means what number multiplied with itself 3 times will give me negative 64. That's negative 4. So what number multiplied with itself gives you 81? It's 9 times 9. What number multiplied with itself gives you negative 81? This is going to be not a real number. This is going to be a complex number, and we will discuss that towards the end of this chapter. Next, we have cube root of negative 27 x to the 9th power. Okay, so cube root of negative 27 is negative 3, because negative 3 times negative 3 times negative 3 is negative 27. And cube root of x to the 9th power. Remember, we're thinking about we have 9 x's. 1, 2, 3, 4, 5, 6, 7, 8, 9. And we are looking for pairs of 3 inside. So we have one pair of 3, another pair of 3, and another pair of 3. 3 x's will come out, which is same thing as x to the 3rd power. For the letter F, we have cube root of 8 divided by 125. Cube root of 8 is 2, because 2 times 2 times 2 is 8. Cube root of 125 is 5. 5 times 5 times 5 is 125. How about x to the 10th power? And we're finding the square root. Okay, think about, we have 10 x's inside. X to the 10th power means we have 10 x's. So 10 times we have that. Now, instead of doing this, let's actually expand this really quick. I want to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're looking for pairs of 2 because there's a 2 in the pocket. 2 is my index. We're looking for pairs of 2 x's inside. How many pairs of 2 x's are there? 1, 2, 3, 4, 5. So 5 x's come out, which is x to the 5th power. Now, what if it was x to the 100? I don't want to write 100 x's and then think about how many pairs I have. I want to find an easier technique. So the easier technique is we can divide the exponent with the index. So 10 divided by 2 is 5. X to the 5th comes out. And the next one, 12 divided by 3 is 4. So x to the 4th power comes out. That means we have 4 groups of 3 x's each when you have x to the 12 inside a cube root. Okay, square root of 64 y to the 20th. Square root of 64 is 8. Y to the 20th means you have 20 y's, and we're looking for pairs of 2. There's going to be 10 pairs of 2 y's. For each pair of 2 y's inside, 1 y will come out of the radical. Square root of 200, I'm going to write it as 2 times 100, and which can be written as 2 times 10 times 10. For a pair of 2 10s inside, 1 10 comes out, and root 2 will stick next to it. 6th root of 64x to the 12. Well, we just talked about 6th root of 64 in the previous page here. 6th root of 64 is equal to 2. You can expand it if you prefer. And for x to the 12th, we have 12 x's inside. We're looking for pairs of 6 or groups of 6 x's. There's going to be 2 of those. So 2x squared. Is it okay to have negative in the odd root? Of course, negative inside the odd root is totally fine. So what number multiplied with itself 5 times will give me negative 32? Well, that's a negative 2, because negative 2 times negative 2 times negative 2 times negative 2 times negative 2 will give me negative 32. So if I multiply negative 2 5 times, I do have negative 32 there. And 15 x's inside. I'm looking for groups of 5. There's going to be 3 groups of 5. I can also do 15 divided by 5. That tells me there's going to be 3 groups of 5 x's each inside the radical. For each group of 5 inside, 1 x will come out of the radical. Now next we have an even root and a negative inside. So that's going to be not a real number. Since we saw in the previous example that the answers to an even root is always positive, so when we are simplifying and we have variables in the radicand, when you have a variable x in the radicand, you don't really know the x can be positive or the x can be negative. We must use absolute value bars if we are taking out an odd power from an even root. Memorize this. This is going to be very helpful, especially when you're moving towards the STEM field calculus. You will end up using this concept again. If you're pulling out an odd power from an even root, we want to make sure that whatever comes out is positive only. So we do need to put the absolute value bars around to make sure it's positive only, so that there's no danger of being negative. There's no need to use absolute value bars when dealing with odd roots, and the answer will always be real even when the radicand is negative. So let's see some examples. Now I want to explain why do we need to use the absolute value bars when we're dealing with the even roots and not when we're dealing with the odd roots. Okay, think about it. So square root of 25. The reason we're trying to say that the square root of 25 is always positive. It's positive only. Here's the problem. Let's take the number. Actually, let's take 64, because 64 is a perfect square and a perfect cube. Okay? So the problem is there's 2 ways of writing 64. I can write it as 8 squared. And if I divide the index with the exponent, 8 comes out. Another problem is I can also write it as negative 8 squared. If I divide the index and the exponent, negative 8 to the first power comes out. And if you look carefully, this is a big trouble, and this is going to fail all the algebra that's been developed so far, because we are trying to say negative 8 is equal to positive 8, which is not true. We know they're far away from each other on the number line. So to avoid this dilemma and this trouble, we put absolute value bars whenever we take out odd power from an even root. Okay, odd power from an even root, so that we know for sure that your answer is positive only. And this is not the trouble with the cube roots, because there's only one way to write cube root of 64. There's only one way you can write it, 4 to the third power. So that means your 4 will come out. You cannot write it as negative 4 to the third power, because that's not equal to 64. That's equal to negative 64. Okay, so memorize this, remember this. Anytime you have variables involved, because your variables can be positive or negative, and you're pulling out an odd power from an even root, you want to make sure it's positive only, and you want to use the absolute value bars around. Right, let's see. Here is an example. I will be pulling out, so if I use the rule of dividing exponent and the index, I'm going to pull out a -8, but I do need to put the bars around to make sure it's positive only. In the next problem, I'm dealing with an odd root, so no need to worry about the bars. Just leave it as -8 only when you're dealing with the even roots. And variable can be positive or negative. Variable can be any real numbers here. So variables, I skipped some examples. Let's go back and do these first, and then we can go further. All right. In this example, the variables can be any real number. So variables are not just positive only, like in the last case we saw. It did say variables are positive only, but now the variables are any real numbers. So first example, if I use the rule of dividing the exponent with the index, x to the first power comes out, and that is an odd power coming out of an even root, so I do need the bars. The next one, I have 3 x's inside, and I'm looking for pairs of 2. It's a square root. 1 x comes out, and that x will get a bar, absolute value bar. The next example, part C, we have x to the 4th inside. So 4 divided by 2, x to the second power comes out. I don't need the absolute value bars because there's no danger of x squared being a negative number. Even if x is a negative number, x squared will be positive, okay? X to the 6th, I'm going to pull out 3 x's, which is an odd power, so I must use the absolute value bars to make sure it's positive only. X to the 8th power square root, x to the 4th comes out, which is positive only, so no need to use the bars. There's no danger that x to the 4th will be a negative number. X to the 9th, well, we're going to pull out x to the 4th, and 1x will be left inside because there's total 9, and we were looking for pairs of 2 x's. X to the 10th, x to the 5th power comes out. Yes, we need the absolute value bars because the danger that if x is negative, then x to the 5th will be negative. So easy way to remember is whenever you are taking out an odd power from an even root, make sure you put the bars, absolute value bars, okay? Next, we have 12, and it's a cube root. No need to worry about the bars, absolute value bars. When you have cube root, odd root, x to the 4th will come out. X to the 6th, no need to put the bars. It's an even power. X to the 3rd, odd root here. X to the 5th, odd root here again. Next, we just talked about this one. We will put the bars around -8, and your answer will be actually +8 because we want to make sure answer to a square root is positive only. Next, we will do 3 divided by 3, the exponent divided by the index. So I'd have -8 as my final answer. 4th root, 16 divided by 4, a to the 4th comes out, b comes out. Well, is it in danger that a to the 4th can be negative? No. Even if a is negative, the 4th power of a will be still positive, so no need to worry about that. But the b has a danger of being negative, so we want to put the absolute value bars. Next, for the letter P, this can be written as x plus 2 squared. And 2 divided by 2, let's divide the exponent and the index. X plus 2 comes out. We want to put the bars and make sure it's positive only. In the next video, we'll talk about domain of radical expressions as well as graphing radical functions.